With a population that has increased more than fourfold in less than 70 years, while only about 4% of the land is arable and more than 60% of food still has to be imported, Egypt urgently had to launch one of the largest agricultural projects of the 21st century, transforming nearly 1 million hectares of the Sahara Desert into a second Nile Delta. This is not just an irrigation project, but an ambition to rewrite the geographic map through engineering. Starting from massive water treatment plants along the Mediterranean Sea, billions of liters of water are pumped through modern canal and pipeline systems, then spread deep into the desert to turn barren sand into vast green oases. So how can a gigantic engineering system recreate a new delta in the middle of the desert? That is what we will explore in today's video. To understand why this project has become urgent, we first need to look at a geographic reality of Egypt. The country has an area nearly equal to the combined size of the US states of Texas and California. But the land that can actually be cultivated accounts for less than 4% of its territory. And that small strip of land has to feed more than 110 million people. The rest, more than 96%, is the barren Sahara Desert, stretching endlessly and almost impossible to farm. Each year, Egypt's population increases by nearly 1 million people. Meanwhile, land cannot expand on its own, and agriculture cannot move beyond the ancient delta region. This has pushed Egypt past Indonesia to become one of the world's largest wheat importers, tying food security closely to developments beyond its borders. But Egypt's limitations are not only about land. About 97% of the country's fresh water comes from the Nile itself, a river more than 6,600 kilometers long that flows through multiple countries. Most of its flow originates from the Ethiopian highlands outside Egypt's territory. That means the fate of more than 110 million people depends on a river that does not entirely belong to them. For that reason, before even thinking about bringing water across the desert, Egypt tried to maximize every possible water source. First, the country invested heavily in reusing domestic and agricultural wastewater over 4 decades. At the same time, Egypt expanded desalination facilities along the Mediterranean Sea and the Red Sea. However, both of these solutions have clear limitations. Seawater desalination consumes large amounts of energy and operational costs. Meanwhile, wastewater reuse only improves water efficiency, but cannot create a new water source at a large enough scale. As a result, these costly efforts were still not enough to solve the food security challenge. The country needed a bigger step, a shift in how water is transported and distributed on a national scale. That is when the new delta was born. More than 10 billion USD was invested into a massive canal system, carrying water deep into the desert and opening up more than 200,000 hectares of new farmland outside the Nile Delta region. But there is one detail many people misunderstand. The new delta does not actually take water directly from the Nile River. Most of the water comes from the agricultural drainage system of the Nile Delta, collected and treated at massive facilities such as Al Hammam before being pumped back into the desert. In other words, Egypt is not just bringing water into the desert, it is recycling its entire irrigation system. In 2021, the new Delta project officially broke ground. More than 12,000 workers and hundreds of heavy machines operated almost 24/7. Turning the area into a massive construction site in the middle of a sea of sand. The first step was stabilizing the ground, because building on constantly shifting sand is no small challenge. Hundreds of bulldozers continuously leveled sand dunes, cutting down high ridges and filling low areas to create a foundation stable enough for constructing the canal route. After the ground was prepared, about 70,000 tons of soil and sand were excavated each day and redistributed along the route. The canal bed was designed with a U-shaped cross-section, about 45 meters wide and 7 meters deep, allowing water to flow naturally using gravity alone. At the same time as the excavation, the accuracy of the entire route was strictly controlled. The longitudinal slope was adjusted with an error margin of only about 2 centimeters for every 30 meters, a level of precision almost unimaginable for a structure stretching hundreds of kilometers. Under heat exceeding 45 degrees Celsius, the entire construction site operated like a gigantic machine, constantly moving across the endless sea of sand. But excavating the canal bed was only the first step. In a desert environment, water can seep away and be lost within hours if it is not handled properly. Therefore, the waterproofing and reinforcement stage was considered one of the key factors determining the success of the entire project. After the canal base was stabilized, a layer of fine sand, about 5 centimeters thick, was evenly spread to create a cushioning surface before pouring concrete slabs 10 to 12 centimeters thick in standard sections. Notably, this sand layer also helps reduce the risk of concrete cracking, thereby limiting water loss, something that could otherwise waste millions of cubic meters of water each year if not properly addressed. Between the concrete slabs, expansion joints were sealed with hot bitumen to prevent leakage and allow the structure to expand and contract under the extreme temperature fluctuations of the desert, where temperatures can range from around 10 degrees Celsius at night to more than 50 degrees Celsius during the day. In areas with weak soil foundations, a waterproof HDPE membrane was installed beneath the concrete and anchored with steel pins to improve long-term durability. In total, more than 124 kilometers of canal were lined with concrete, becoming one of the largest waterproof canal systems in North Africa. From above, the artificial river appears like a bright silver ribbon cutting across the dry golden sea of sand. After the canal bed was fully reinforced and waterproofed, the next step was the art of controlling the flow. To ensure a stable discharge, intermediate regulating reservoirs were constructed along the canal route. Each reservoir covers about 2 hectares, with a regulating capacity of tens of thousands of cubic meters of water, large enough to absorb and smooth out flow fluctuations when water enters the system. The entire system was designed to regulate about 25 cubic meters of water per second, equivalent to more than 2 million cubic meters of water per day, helping the downstream network operate steadily. The reservoir beds were compacted, lined with waterproof membranes, and covered with load-bearing concrete to ensure long-term durability under harsh desert conditions. The inlet and outlet gate systems were designed to allow precise water level control, keeping the entire downstream network operating smoothly and safely. Next came the monolithic reinforced concrete regulating dams, which serve as the central control points of the flow. At each discharge bay, steel pipes with diameters of 2 to 3 meters were installed, precisely aligned and strictly tested before being put into operation. From this point onward, the water no longer flows freely, but becomes part of a system fully controlled by engineering and calculation. After the regulating reservoirs and control dams, the water continues to be distributed deeper inland through a large-scale transmission network. From the main canal, steel pipes with diameters ranging from 1.5 to 3 meters were installed to deliver water to newly developed agricultural areas emerging in the desert. Each pipe section, dozens of meters long, was precisely aligned before being welded in a 360-degree seam, then inspected using ultrasonic testing to ensure no leakage occurs during long-term operation. The entire system was installed underground, helping reduce evaporation losses and protecting the structure from harsh climatic conditions. Upstream, near the Nile River, a smart pumping station serves as the central water supply hub. High-capacity pumps combined with variable frequency drive inverters allow real-time flow adjustment to match demand at different times. A network of pressure, water level, and flow sensors continuously transmits data to the control center, where parameters are monitored and automatically fine-tuned. From that moment, Egypt began rewriting its destiny, not only adapting to the desert, but transforming the desert into the green color of life. As water began to stabilize within the canal and pipeline system, the transformation gradually became visible from above. Amid the vast stretches of yellow sand, green circles appeared as the clearest signature of the project. These are fields irrigated by center pivot systems, long metal arms rotating slowly like the hands of a clock, distributing water evenly across every meter of land. From a barren landscape, more than 200,000 hectares of new land are now being formed and brought into cultivation. Beyond crops, large-scale livestock complexes are also being built in parallel, each facility capable of raising up to 6,000 cattle within a centralized operational system. The entire model is designed as a closed-loop cycle. Livestock feed is produced on-site, water is distributed directly from the main network, and the final products are fed straight into the domestic supply chain. On these newly reclaimed lands, wheat is considered the most important test for the new delta. Not because it is easy to grow, but because it requires high stability in water supply, salinity levels, and soil nutrients. Desert sand contains almost no organic matter, so before each planting season, the soil must be improved with fertilizers and monitored through electrical conductivity control to prevent salt accumulation. In pilot areas, initial yields can reach about 5 to 7 tons per hectare, comparable to many traditional agricultural regions in Egypt. If only 50,000 hectares of the more than 200,000 newly developed hectares achieve this yield level, production could reach 250,000 to 350,000 tons of wheat per harvest, a figure that is no longer symbolic, but one that could directly affect the country's supply-demand balance. More importantly, the goal is not a single successful harvest, but maintaining stable productivity across multiple cycles. If the soil does not become salinized and the irrigation system maintains nutrient balance for 5 to 10 years, it would prove that the desert can be transformed into a long-term production base rather than just a short-term experiment. The transformation of the desert creates a compelling sense of possibility. But behind the newly formed fields lies a larger question. Can this model be sustained in the long term? Pumping millions of liters of water into a hot, arid climate comes with significant costs. Pumping stations consume considerable amounts of energy to maintain a stable flow. Under temperatures that can exceed 45 degrees Celsius, the risk of evaporation is constant, reducing water use efficiency. In addition, if not carefully managed, soil salinization could become a serious challenge in the years ahead. Therefore, the question is not only whether the project can operate, but whether it can be sustained for decades without degrading resources or surrounding ecosystems. Lessons from land reclamation projects in arid regions show that water management requires a delicate balance between engineering and ecology. At a national scale, the new delta is not just infrastructure made of concrete and steel. Its success will depend on how Egypt manages every drop of water in the future. Egypt is not the first country to attempt bringing water across the desert. As early as the 1980s, Libya launched the Great Man-Made River, one of the largest water conveyance systems in the world. The project built thousands of kilometers of massive pipelines, many sections with diameters of up to about 4 meters, buried deep beneath the sands of the Sahara to transport groundwater from fossil aquifers in the south to coastal cities in the north. It was a monumental project both technically and in scale. The water Libya tapped was fossil groundwater, stored underground for thousands of years and almost never naturally replenished. The entire system lies mostly underground, reducing evaporation losses, but relying entirely on a finite reserve. Egypt has chosen a different path. Instead of hiding beneath the sand, it has constructed massive open canals across the desert surface, combining concrete channels, regulating reservoirs, smart pumping stations, and modern distribution networks. The New Delta project is not just an artificial river. It is an effort to redefine the limits of geography and engineering. From a nation once constrained by a single river, Egypt is now attempting to expand its living space deep into the Sahara Desert. As climate change reshapes the global map of water, projects like this may become the precedent of the 21st century. What do you think about this direction? And in your opinion, which country will be the next to challenge the limits of the desert?